The sound comes first. Not gunfire, not engines, not the whistle of falling shells, but the rhythmic hammering of metal on metal, echoing across the dark waters of the Rhine River. March 7th, 1945. 2:47 in the morning. The temperature hovers just above freezing, and fog rolls off the water like ghostly fingers reaching toward the German heartland. On the western bank, American engineers work by the pale light of shielded lamps, their breath forming small clouds as they bolt together steel panels with methodical precision. Each hammer blow carries across the water a funeral bell for the Third Reich. In the distance, beyond the tree line on the eastern shore, German sentries strain their ears against the darkness. They know the Americans are there. What they do not yet comprehend is that these men in olive drab uniforms are not merely soldiers. They are architects of Germany's defeat. These builders of bridges will carry the weight of an entire army across the last natural barrier protecting the fatherland. The Rhine had always been more than a river to the German mind. It was a moat around a fortress, a liquid wall that had protected Germanic tribes from Roman legions 2,000 years before. In the winter of 1945, as Allied forces pressed against Germany's western borders, Wehrmacht generals gazed across its dark waters with something approaching confidence. The Americans, they reasoned, were factory workers and farmers masquerading as soldiers. They might have numbers, they might have industrial might, but they lacked the technical sophistication, the engineering precision that German military doctrine demanded. Building bridges under fire? Across a river 980 feet wide, with currents strong enough to drag away a Sherman tank? Impossible. The Rhine would buy them time, perhaps months, to prepare defenses, to rally the Volkssturm, to organize a miracle. They were about to discover how catastrophically wrong they could be. The genesis of their miscalculation lay in a modest office in Christchurch, England, 4 years earlier. There, a soft-spoken civil servant named Donald Bailey had sketched an idea on the back of an envelope. A bridge made of interchangeable steel panels, light enough for 6 men to carry, strong enough to support a tank. The concept seemed almost childishly simple. Standardized components that could be assembled without cranes, without specialized tools, without the elaborate preparations German engineers believed essential for serious bridge construction. British military officials, initially skeptical, authorized a test. Bailey's prototype went up in a matter of hours. By 1942, his revolutionary design was rolling off production lines at a rate of 500 sets per month. What Donald Bailey had invented was not merely a bridge. It was a philosophy of engineering that would transform modern warfare, where German doctrine emphasized complexity, precision, and time-intensive preparation. Bailey's approach embraced simplicity, speed, and adaptability. His bridges could be assembled by ordinary soldiers following basic instructions. They required no special foundations, no complex anchorages, no weeks of surveying and calculation. In Bailey's revolutionary vision, a bridge was not an architectural monument, but a tool, as standardized and replaceable as a rifle or a field radio. American engineers embraced Bailey's concept with the enthusiasm of converts to a new religion. By 1944, U.S. Army engineering schools were teaching Bailey Bridge construction as standard curriculum. Combat engineer battalions drilled endlessly in the art of assembling the prefabricated sections, timing themselves against stopwatches, competing to shave minutes, then seconds, off their assembly times. The best crews could erect a single-span Bailey Bridge in under 6 hours. The most experienced could do it in the dark, under artillery fire, working from memory and muscle reflex alone. But bridges were only part of the story. American engineering philosophy had been revolutionized by the industrial demands of a global war. Assembly line techniques pioneered in Detroit automobile plants now governed the construction of temporary military infrastructure. Pontoon bridges could be manufactured in sections, shipped anywhere in the world, and assembled by crews who had never seen that particular river before. Treadway bridges, floating roadways supported by pneumatic pontoons, could be deployed and anchored in a matter of hours, then disassembled and moved to a new location when tactical requirements changed. The Germans, products of an engineering tradition that prized individual craftsmanship and site-specific solutions, could not fathom this industrialized approach to military engineering. Their own bridge-building doctrine required weeks of reconnaissance, detailed surveys, custom-designed foundations, and specialized construction teams working with site-specific plans. When German engineers built a bridge, they built it to last for decades. When American engineers built a bridge, they built it to last until the next tactical objective was secured. And then they built another one. This fundamental difference in military philosophy created a gap in understanding that would prove fatal to German defensive planning. Wehrmacht intelligence officers studying captured American equipment focused on individual specifications, load capacities, span lengths, material strengths, while missing the larger picture. They saw the components, but not the system, the tools, but not the revolution in thinking that made those tools possible. As 1945 opened and Allied forces approached the Rhine, German defensive strategy assumed that river crossings would follow traditional patterns. The enemy would require weeks to prepare, would need specialized equipment and favorable weather, and would be vulnerable to counterattack during the lengthy preparation phase. German commanders positioned their reserves accordingly, planning to mass forces against predictable crossing points during the window of vulnerability they expected American preparations to create. The first sign that their calculations might be wrong came on March 7th, when Lieutenant Karl Timmerman of the 27th Armored Infantry Battalion led his men across the damaged but still standing Ludendorff Bridge at Remagen. The bridge had been prepared for demolition, its destruction prevented only by the failure of German explosive charges to completely collapse the span. American engineers raced across the partially damaged structure, cutting wires and removing unexploded charges, while German artillery pounded their positions from the heights on the eastern shore. But the real shock was not the capture of an existing bridge, it was what happened next. While German commanders focused their attention on destroying the Ludendorff span, American engineers were already at work on alternatives. Within hours, the 51st and 291st Engineer Combat Battalions had begun construction of a heavy pontoon bridge upstream from Remagen. Working under constant artillery fire, with German aircraft strafing their positions and floating mines drifting downstream toward their work sites, these men performed feats of engineering that would have been considered impossible by traditional military doctrine. The pontoon bridge took shape with mechanical precision. Pneumatic floats were inflated and positioned in the swift current. Steel decking was rolled into place. Anchor cables were dropped and secured against the river bottom with specially designed weights. Bailey panels filled with rocks, each anchor weighing several tons. The entire operation proceeded according to a predetermined schedule, each step flowing seamlessly into the next, each component fitting together like parts of a vast machine designed for a single purpose: moving American armor and infantry across the Rhine as quickly as possible. German artillery observers, watching through field glasses from concealed positions on the eastern heights, could hardly believe what they were seeing. The Americans were building bridges the way their factories manufactured trucks, with standard components, following standard procedures, apparently immune to the traditional constraints that govern such operations. When German shells found their mark and damaged sections of the pontoon bridge, American repair crews moved in immediately, replacing damaged floats and decking with spares that seemed to materialize from nowhere. Behind the immediate tactical situation, a larger drama was unfolding. Every major river crossing in military history had required extensive preparation time. Weeks or months of logistical buildup, detailed reconnaissance, specialized equipment designed for specific geographic conditions. The American approach inverted this traditional pattern. Instead of adapting their engineering to match geographic constraints, they adapted geography to match their engineering. Rivers became obstacles to be overcome in hours, rather than barriers requiring months of preparation. The psychological impact on German defenders was profound. Soldiers who had been told they were fighting behind an impregnable barrier now watched American tanks rolling across bridges that had been empty of water just days before. Luftwaffe pilots, ordered to destroy these temporary crossings, found their targets defended by concentrated anti-aircraft fire and protected by smoke screens that made precision bombing nearly impossible. Even when German attacks succeeded in damaging or destroying sections of American bridges, the structures reappeared with bewildering speed. General George S. Patton, commanding the Third Army, understood the psychological dimension of the engineering revolution his forces were demonstrating. On March 22nd, as his 5th Infantry Division prepared to cross the Rhine at Oppenheim, Patton emphasized speed over stealth. He wanted the Germans to see American bridges appearing overnight, wanted enemy commanders to wake each morning to discover new crossing points that had not existed the day before. The Oppenheim crossing embodied everything German military planners had failed to anticipate about American engineering capabilities. Patton's forces moved quickly and quietly to the river's edge, carrying assault boats that had been stockpiled far behind the lines since the previous autumn. Navy and Coast Guard crews, veterans of the Normandy landings, operated landing craft that had been trucked hundreds of miles from supply depots to appear precisely where and when the tactical situation demanded them. The first wave of American infantry crossed in darkness, encountering only light resistance from surprised German defenders. But the real demonstration was yet to come. As dawn broke on March 23rd, German observers on the eastern shore saw American engineers already at work on permanent crossing sites. Bailey bridges began taking shape with mechanical precision. Pontoon bridges appeared as if assembled by invisible hands. Heavy equipment bridges capable of supporting Sherman tanks stretched across waters that had been empty just hours before. Each bridge represented not merely a tactical achievement, but a philosophical revolution. German engineering doctrine, rooted in 19th-century traditions of craftsmanship and site-specific solutions, had been rendered obsolete by American mass production techniques and standardized components. Where German engineers would have spent weeks surveying, calculating, and preparing custom solutions, American crews simply followed standardized procedures using interchangeable parts. The speed of American bridge construction created a tactical tempo that German defenders could not match. Traditional defensive doctrine assumed that river crossing operations would unfold over days or weeks, providing time for reserves to be repositioned, for concentrated counterattacks to be organized, and for defensive lines to be strengthened. American engineers collapsed these time intervals to hours. By the time German commanders had assessed the threat at one crossing point, American forces were already streaming across bridges at 3 or 4 other locations. Major General S. Leroy Irwin's 5th Infantry Division, spearheading Patton's Rhine assault, found itself fighting on the eastern shore, while engineers behind them continued expanding and reinforcing the bridges that had made their advance possible. The division's after-action reports noted with amazement the continuous stream of supplies, reinforcements, and heavy equipment flowing across bridges that seemed to multiply overnight. German tactical doctrine had anticipated fighting for every crossing point, turning each river into a killing ground where American forces would be channeled into predictable approach routes and destroyed by concentrated fire. Instead, German defenders found themselves facing multiple crossings simultaneously, each protected by rapidly constructed air defenses and supplied through what appeared to be an endless network of temporary bridges. The engineering techniques that enabled this transformation had been developed through hard experience in earlier campaigns. American engineers had learned their trade-building bridges across the rivers of France, replacing spans destroyed by German demolitions or Allied bombing. They had perfected their methods under fire in the Ardennes, constructing temporary crossings while German artillery zeroed in on their positions. By 1945, these men possessed a level of practical expertise that no amount of theoretical study could match. Lieutenant Colonel H.F. Cameron, commanding the 164th Engineer Combat Battalion at Remagen, later described the almost industrial efficiency with which his men approached their work. "We figured there was only one way to anchor our net and prevent creeping," he recalled, referring to the protective barriers designed to stop German floating mines from reaching the bridges. "We took 4 Bailey panels, welded them together, and then lined them with reinforcing steel wire and filled boxes with rock. With the 4 Bailey panels at 580 pounds a panel, filled with rock, we figured there were 6 or 8 tons in each one of those anchors." Cameron's matter-of-fact description captured the essence of the engineering revolution that German generals had failed to comprehend. American engineers did not simply react to tactical challenges, they systematically solved them using standardized components and proven techniques. When German tactics called for floating mines, American engineers deployed weighted nets. When German artillery targeted bridge approaches, American crews installed smoke generators. When German aircraft attacked during daylight hours, American engineers worked at night using specially developed searchlights that illuminated work areas, while blinding enemy observers. The cumulative effect of these innovations transformed individual tactical situations into strategic victory. German defensive plans that had assumed weeks of warning time were overtaken by American bridges that appeared in hours. Reserve forces positioned to counterattack predictable crossing points found themselves outflanked by bridges at unexpected locations. Artillery positions sited to cover traditional approach routes were bypassed by American armor streaming across rivers where no crossing had existed the day before. The psychological impact extended beyond immediate tactical consequences. German soldiers, indoctrinated to believe in their technological and organizational superiority, found themselves confronting evidence of American engineering capabilities that shattered fundamental assumptions about the war. These were not the industrial draftees and farm boys that German propaganda had described. These were skilled professionals, executing complex operations with clockwork precision. The engineering revolution that American forces demonstrated at the Rhine represented more than tactical innovation. It embodied a fundamental shift in the relationship between military objectives and technological capabilities. Traditional military engineering had adapted tactics to match available technology. American engineering adapted technology to match tactical requirements. If a river needed to be crossed, bridges would be built to cross it. If existing bridge designs were inadequate, new designs would be developed. If standard procedures were too slow, new procedures would be improvised. This philosophical approach extended far beyond bridge construction. American forces had revolutionized military logistics through standardized components, interchangeable parts, and mass production techniques borrowed from civilian industry. The same principles that enabled Detroit to produce thousands of identical automobiles now governed the production of pontoon bridges, Bailey spans, and treadway sections. Complex military equipment became as standardized and replaceable as ammunition or field rations. German military culture, rooted in traditions of individual expertise and craft specialization, could not adapt quickly enough to match this industrialized approach to warfare. German engineers remained highly skilled at solving individual problems through innovative design and careful execution, but American engineers solved classes of problems through systematic application of proven techniques using standardized equipment. The Rhine crossings of March 1945 became a masterclass in this new form of military engineering. At Boppard, the 87th Infantry Division encountered heavy resistance from German 20mm guns positioned on the heights above the river. American engineers responded by repositioning their bridge site downstream, beyond the range of the enemy weapons, and constructing their crossing under the cover of smoke screens that made accurate German fire impossible. At St. Goar, the 89th Infantry Division faced similar challenges from German defenders who had learned to anticipate American tactics. Again, American engineers adapted, using Navy landing craft to ferry initial assault waves while bridge construction proceeded at alternative sites. When German artillery damaged one bridge, replacement sections were already in transit. When German aircraft attacked during construction, anti-aircraft weapons that had accompanied the engineers from their departure points opened fire immediately. Each crossing demonstrated the same pattern: German defenders employing traditional tactics against American forces using revolutionary techniques. German commanders who had expected weeks of preparation time found American bridges appearing overnight. German artillery observers who had registered their guns on predictable crossing points found American engineers building bridges at unexpected locations. German reserve forces positioned to exploit the vulnerabilities of traditional river crossing. Operations discovered that American tactics had eliminated those vulnerabilities. The technical achievement represented by these crossings becomes clear when measured against historical precedents. Caesar's famous bridge across the Rhine in 55 BCE had required 10 days to construct using Roman engineering techniques that were considered miraculous for their time. Montgomery's carefully planned Rhine crossing in late March 1945 required weeks of preparation and involved overwhelming concentrations of men and material. American engineers, working under enemy fire with standardized equipment, were achieving comparable results in hours. The secret lay not in individual brilliance, but in systematic application of industrial principles to military engineering. Bailey Bridge components were manufactured to such precise tolerances that sections produced in different factories could be assembled without modification. Pontoon bridge elements were designed to specific load and buoyancy requirements that made tactical planning more predictable. Treadway bridge sections could be deployed by crews who had never seen that particular river, but who understood the standard procedures for anchor placement, current assessment, and load distribution. American engineer training reflected this systematic approach. Combat engineer battalions drilled endlessly in bridge construction techniques, timing themselves against stopwatches, competing to achieve ever faster assembly times. Officers studied not individual bridge designs but classes of engineering problems, learning to select appropriate solutions from a menu of standardized options. Enlisted men mastered not specific construction trades but systematic procedures that could be applied regardless of geographic or tactical circumstances. This training philosophy paid dividends when American forces reached the Rhine. Engineer crews who had practiced Bailey Bridge assembly and training camps in Louisiana found themselves applying identical techniques under artillery fire in Germany. Officers who had studied river crossing procedures in classrooms at Fort Belvoir discovered that their theoretical knowledge translated directly into practical results when applied to the fast-flowing waters of the Rhine. The cumulative result was an engineering capability that German military planners had not anticipated and could not match. American forces could move from tactical decision to tactical execution with unprecedented speed. When Patton decided to cross the Rhine at Oppenheim, his engineers already possessed the equipment, the training, and the procedures necessary to accomplish the mission. When German defenders attempted to disrupt American crossings, American engineers simply implemented contingency plans that had been developed. Through months of training and experience, the broader implications of this engineering revolution extended far beyond the immediate tactical situation at the Rhine. American forces had demonstrated that modern warfare would be decided not by individual acts of heroism or brilliant tactical insights, but by the systematic application of industrial capabilities to military problems. Victory would belong to the force that could most efficiently convert strategic resources into tactical capabilities. German military culture, shaped by romantic notions of individual prowess and technological superiority, proved inadequate to compete with American systematic efficiency. German soldiers remained individually courageous. German weapons remained technically sophisticated, and German tactical doctrine remained theoretically sound. But German forces could not match the speed, scale, and consistency with which American forces converted strategic advantages into tactical results. The Rhine crossings became a symbol of this larger transformation, like warfare. Each bridge that appeared overnight represented not merely a tactical achievement, but evidence of a military system that had learned to think in industrial terms. American forces had become a machine for converting strategic resources into tactical victories. And the machine's efficiency was overwhelming German defenders, who still thought in terms of individual battles, rather than systematic campaigns. As the march days lengthened, and American forces consolidated their bridgeheads on the eastern shore of the Rhine, the psychological impact on German resistance became increasingly apparent. Soldiers who had been told they were defending impregnable positions now watched enemy tanks rolling across waters that had been empty just days before. Officers who had planned defensive operations based on traditional assumptions about river crossing timelines found their carefully prepared positions outflanked by American advances that proceeded according to an accelerated schedule. The collapse of German confidence was reflected in prisoner interrogation reports filed by American intelligence officers. German soldiers expressed bewilderment at the speed with which American forces had overcome what they had believed was the last natural barrier protecting the fatherland. German officers, trained to think in terms of lengthy preparation phases and vulnerable crossing operations, could not comprehend tactical doctrines that eliminated those phases of vulnerability. The engineering achievement that made this transformation possible remained largely invisible to contemporary observers. War correspondents wrote about American courage and determination, about German resistance and eventual collapse, about the tactical significance of various crossing points. Few recognized that they were witnessing a revolution in military engineering that would reshape modern warfare for decades to come. Yet the revolution was real, and its implications profound. American engineers had not merely built bridges across a river. They had built a bridge across time, connecting traditional military engineering to the industrial future of warfare. Their hammers, striking steel in the darkness of March 1945, were beating out the rhythm of a new age in which military victory would belong to the force that could most efficiently systematize the business of war. The sound fades now, carried away by the current of the Rhine and the passage of decades. But the lesson remains, encoded in the twisted remains of the Ludendorff Bridge, in the archives documenting Bailey Bridge construction times, in the faded photographs of American engineers working by lamplight while German shells fell around them. They had proved that warfare was not romance, but engineering. Not individual heroism, but systematic efficiency. Not ancient tradition, but industrial innovation. German generals had laughed at American engineers, dismissing them as amateur tinkerers unworthy of serious military consideration. By April 1945, as American armor rolled deeper into the collapsing Reich across bridges that had risen overnight from the dark waters of the Rhine, those same generals understood that they had witnessed something unprecedented in military history. The Americans had not simply built bridges, they had built the future, one standardized steel panel at a time, while the old world's certainties crumbled into the river below. In the end, the Rhine had indeed protected Germany, but not in the way Wehrmacht planners had intended. It had protected the Reich's enemies from understanding the true extent of their own capabilities, until the moment those capabilities were unleashed. The dark waters reflected not German strength but American ingenuity, not ancient barriers but modern solutions, not the past but the inexorable approach of a future in which victory would belong to those who understood that war was not art but science, not inspiration but systematic application of industrial might to military necessity. 3D bridges rose overnight because the men who built them had learned to think overnight, to compress weeks of traditional preparation into hours of systematic execution, to replace individual craftsmanship with mass production efficiency, to substitute American industrial might for European military romanticism. They were engineers, and they had engineered victory itself, span by span, rivet by rivet, bridge by bridge, until the river that was supposed to protect Germany became the highway for its defeat.